Welcome to another lecture in Intro Psych. This is supposed to be a lecture on the scientific methods in psychology, but really I designed this lecture for the everyday consumer of information, right? I want you to not just passively absorb information that you hear about, especially if it's based on research. Rather, I want to equip you with some knowledge about the basics of research so that you can more critically evaluate the evidence that you're presented with and decide if it's actually representative of what the media or whoever is sharing the results with you says it is. All right, so today's dad joke of the day is, what type of parasites do senators have? Politics. So many of you may not think psychology is a science. You may have been told psychology is considered as quote-unquote a soft science, but really if you look at what makes science a science, psychology as a field has all the makings of that, of those criteria. So one thing about psychology and research in psychology is that it differs slightly from the other scientific fields you might be familiar with, such as biology or chemistry or physics. Historically, unlike those other fields, psychology started deliberately as an attempt to better understand the human mind. The other thing that differs about psychology compared to other fields is that it has special ethical considerations. In psychology, we often study people as our subject matter, and so when we're dealing with people, we have strict limits for what's allowable to be done with humans and what's not. There are actually federal laws controlling what kinds of research is permitted and not permitted with human subjects. All sciences gather evidence using the scientific method. It might start off with a careful observation, but then based on that careful observation, a scientist might develop a hypothesis. You might have heard a hypothesis is an educated guess, and while that might be correct, in the context in which you learned that, hypothesis in this instance is a predictive statement attempting to explain why what was observed actually was. And so hypotheses are testable. What that means is we can design experiments to test if our prediction is correct or not. So it's a little bit different than an educated guess. It may be based on prior research, but a hypothesis in this case is an attempt to explain an observation, and it's something that can be tested. Oftentimes, hypotheses are tested using methodologies that don't involve what's called confounds or biases. So when we design experiments, we want to make sure that we are designing it in such a way that nothing other than what it is we are trying to study is influencing the results. When you have a confound, it represents a variable or a factor that's affecting your results that is unrelated to what it is you're studying. Similarly, scientists are humans and they might have biases in their perspectives and ways of thinking. And so when we're doing research, when we are testing a hypothesis, we want to make sure that it does not involve any confounds or biases on the part of the experimenter. Each method, and this is referring to kind of the technique we're going to be using to study or test the hypothesis, has its strengths and weaknesses. And so it's really important when you're testing a hypothesis that you don't simply test it in one way. It's important to use a variety of techniques to ensure that your results are actually valid or sound or have some truth to them. Getting the same conclusion when you end up testing your hypothesis in different experiments or different techniques validates it. It confirms that hypothesis. So the word validation, affirm, means to affirm your hypothesis. It makes your hypothesis more credible. Your results, which are the outcome of your experiment, allows you to determine whether your hypothesis was actually correct or not. Unfortunately, oftentimes what happens is, because of biases, you hope that that's not the case, results are often interpreted, which is the step in the scientific process where the researcher determines the meaning behind the results. However, if there are biases or the researcher has a particular agenda, they might interpret the results to kind of go in line with their thinking and make a bigger deal out of it than it really needs to be. So interpretation, while it's an important component of the scientific process, unfortunately, it is the point at which the greatest amount of subjectivity can influence the experiment or the science. All research should be replicatable. What that means is that any other researcher can follow exactly the same procedures that you did in your experiment and get the same results. Oftentimes, fraudulent research is discovered because somebody else attempted to replicate the research and wasn't able to. So when you're able to replicate somebody else's work, you can also gain more credibility for the research that you did. If you're unfamiliar with the scientific method, here's kind of like a bare bones nuts and bolts behind the scientific method. It often starts with observations that leads to an explanation of those observations, a hypothesis that can be tested using an experiment. That hypothesis is tested through research. You gain results from that research, and those results either support or negate the hypothesis. Okay, so you'll see here that research or the scientific method tends to be what's called a cyclical process. It kind of feeds back on itself, and it might either support the hypothesis, which may result in further inquiry into that original observation, or a revision may be necessary of the hypothesis, which would require additional research. And so didn't mean to jump ahead there. I clicked a button too many times. Another way to kind of explore this is you have your hypothesis. You've tested your hypothesis, designing an experiment. You either get results that support your hypothesis, and then you can have confidence in your hypothesis that your explanation was correct, or your results don't support your hypothesis, in which case you can't be sure that the explanation you originally had was correct, and so you either need to modify that hypothesis, so change it in some way, or get rid of it completely, depending on how far away your results were from the hypothesis. When we're evaluating scientific theories, it's important to keep a few things in mind. The term hypothesis is often used interchangeably with theories, but theories are very different from hypotheses. They're related to each other, but theories represent kind of broad explanations or models that can fit many different observations. And we may use those theories to generate different hypotheses, but theories represent kind of broad understanding or explanations, and multiple different hypotheses can feed into one theory. What's important about theories is that it needs to have the least fewest assumptions as possible to be correct. And so it's really important that scientists agree how theories should be evaluated, because if they don't agree, then you might have theories out there that aren't really kind of strong or sound or credible. And so it's really important that scientists, especially if they're coming up with a new theory, follow what's called the burden of proof. So burden of proof refers to the fact that anyone who's developing or proposing a new theory has the burden to demonstrate or provide proof that the theory is correct. Okay, so let's say I am coming up with a new theory that the color of the grass is not actually green, it's purple, but our eyes change that color to represent green. Okay, so I'm developing a new theory. It is on me to provide the evidence to support that particular claim, that new theory. If I cannot demonstrate that my theory is correct, then I can't necessarily, then it can't be a new theory, right? So the burden of proof, or the burden of providing evidence for a new theory, rests on the person making the new claim. A well-formed theory is what's called falsifiable. So let me unpack for you what falsifiable means. A falsifiable theory, or to be able to, let me step back a second. So the point of research is to falsify incorrect theories. So we want to provide evidence or show that a theory is not correct, because a good theory withstands being falsified. So what does it mean to be falsifiable? So you can imagine evidence that would go against the theory. And so the theory should be stated in such a way, in such clear and precise terms, that we could imagine evidence that would go against it. We can imagine something that would count as evidence against that theory. So let's take, for example, the theory of gravity, right? You are all familiar, or hopefully familiar, with this idea, the theory of gravity, that everything is pulling us towards the earth. So what would evidence against the theory of gravity look like? How could we falsify the theory of gravity? So I would pause the lecture and think about it for a little bit. I would imagine, if you've thought about it, that you came up with the answer that if the theory of gravity wasn't correct, we would all be floating, that we wouldn't all be pulled to the surface of the earth. So even though the theory of gravity is correct, is true, we can imagine evidence against it. So a well-formed theory is falsifiable because we can imagine evidence that would go against it, even if the theory is true. So Freud's theory on dreams, for example, he argued that dreams held meaning and contained people's most unconscious desires and wants. Those dreams, unfortunately, are not falsifiable, so it does not represent a very good theory. Another important aspect of theories is something called parsimony. Parsimony represents the simplest explanations for an observation or evidence. So when we come up with an explanation for something, it should avoid including new assumptions. And so parsimony involves using kind of common sense to come up with an explanation. When we are doing research, it's also important to keep an open mind, right? It's important to be open-minded because there might be new evidence that we hadn't considered before. So it's important to not assume that previous theories are kind of set in stone, that there might be evidence against those theories in the future, but it's also important to utilize common sense and not be gullible about any new theory that shows up. And so parsimony, which is kind of finding the simplest explanation for something, prevents us from accepting some crazy, outlandish new theories. So take, for example, you come into a room and you see that a picture on the wall that was straight before is now hanging at an angle. You consider possible explanations for what could have caused it. Now, the question is, could it have been a ghost? Or was it something else? If we're using parsimony, we shouldn't explain that picture being tilted as being caused by a ghost, because that requires a new assumption, the existence of ghosts. And I'm not, kind of bursting anyone's bubble who believes in ghosts, but there's no theory supporting the existence of the ghosts. And so the fact that the picture is hanging on the wall at an angle is the most parsimonious explanation is not that it was a ghost. Instead, it could easily have been that somebody bumped into that picture, causing it to be crooked. Or if you live in a town where, you have lots of semi-trucks going by, they shake the house. That might have caused the picture to be at an angle. Those hypotheses don't require any new assumptions, so they represent the more parsimonious explanations for this particular observation. If you have ever seen these videos by Zach King, what's really cool is that he uses visual illusions to try to get us to believe certain things are true, and so they do not represent the most parsimonious explanations for the things that we are seeing, but they're still entertaining to watch. I would have shown this video in class, but because this is a recorded lecture, I'm not going to play it. I would encourage you to search Zach King videos, and you'll see some really entertaining magic, so to speak. But they are more visual illusions than they are reality, because they would require us to believe or make many assumptions about what's happening than what is actually parsimonious. All right. So some general research principles, and again, just as a reminder, I'm sharing this information with you not because I think you're going to be doing research in the future, but rather I want you to think about the ways in which research is conducted so that when you encounter evidence from research, you will enter it with some idea of how research should be done. So most research tends to use the scientific method, but they face unique problems in psychology, right? So we often tend to study things that aren't easily observed. And as we've mentioned before, research involves studying what's observable. And so in psychology, we often have to use what's called operational definitions. Operational definitions represent kind of behaviors or definitions for psychological constructs that may not easily be observed. And so it describes what researchers to look for to measure something abstract like emotion or depression or anxiety. It allows them to measure it and give it a numerical value so it can be studied. Operational definitions sometimes represent kind of like a survey tool that people can take to assess them for things like anxiety, but you can also have operational definitions for emotions, for example. If you wanted to study something like how does stress impact friendliness, which is a research topic that a psychologist could study, you have to ask, how are you going to measure stress? There are many different ways you can do that. How would you measure friendliness? What does that look like? In order to be able to be replicated, you as the researcher would have to come up with operational definitions for something like friendliness, so that in the future, if somebody was trying to replicate what you found, they would be able to follow the procedures associated with friendliness to ensure that they're actually measuring friendliness. So just to reiterate, operational definitions are descriptions of behaviors or procedures to measure psychological variables that often aren't easily measured. And they represent descriptions, right? It allows us to describe what something would look like so that it could be measured and then replicated. The other feature that psychologists kind of struggle with are population samples, deciding who to study. So we can't study every single person on this planet. It's just not feasible. And so instead, what we do is we take a sample of the larger population and then assume or hope that our sample represents the larger population, so that anybody that we select for our sample actually matches what we would see in the general population. The problem is that we might accidentally choose people who are unique in some way, resulting in a bias within our sampling. So there's much more to sampling than what we can cover in this course, but it's also really important to look at who the researchers studied as their subjects, and then see whether they are making generalizations to the general population, and if those subjects are representative of the population. So there are many different ways to study human beings. One way to do it is something called observational research design. Most research starts with observations and descriptions of those observations. What's happening and under what circumstances, so we can see potentially the relationship between different factors or variables that are being studied. Observations are one way to answer these types of questions, to determine what's happening, what behaviors are occurring, and under what circumstances. We can do them in what are called naturalistic observations, and this is great because what we're doing with the naturalistic observations is we are allowing the behavior to occur in the natural setting, and then just paying attention to what might be triggering those behaviors or what might be influencing those behaviors to better understand or come up with a hypothesis for an explanation for that behavior. What's great about naturalistic observations is because they're occurring in the natural setting, we know that they're going to occur. Whatever conclusions we draw from these naturalistic studies, they can be applied to the general population because they're occurring in their natural setting. Surveys are most often used by psychologists. They represent kind of a paper and pencil way to gather results. We use surveys to try to determine the prevalence of beliefs or attitudes or behaviors based on people's self-report. I mentioned self-report because there's no way to know for sure if they're being truthful or not, but we have to make the assumption that they are when we are conducting survey results. Finally, something that you might be unfamiliar with is something called correlational studies. So naturalistic observations, surveys, and correlational studies all represent observational research designs. A correlation represents a measurement of two variables or factors. So we're measuring two different things and then determining if they are related in some way or not. Most often, you're going to find correlational studies in the research that media tends to report, especially when it comes to human studies. When we conduct a correlation, oftentimes we end up doing statistics on the data that we get for a correlation, and those statistics spit out a number called the correlation coefficient. The correlation coefficient represents a mathematical estimate of the relationship between those two variables whose relationship you are trying to assess. Correlation coefficients, the values, range from -1 to +1. The closer to 1 your coefficient is, the stronger the relationship between your two variables or factors being measured. What this allows us to do is make predictions of how the variables behave with respect to each other. So for example, there is a positive correlation between age of children and their height. Knowing that there's a positive correlation, especially if we know that what the coefficient is, allows us to make predictions of a child's age simply based on their height, or vice versa. We can use scatter plots to further explore the relationship between two variables. So let's talk a little bit more what I meant by positive correlation. So a positive correlation is typically the relationship between two variables such that as one variable increases, represented here on the x-axis, so too does the other variable, represented here on the y-axis, resulting in kind of like an upward slope of the scatter plot. And the scatter plot is created in the same way that you might create an XY coordinate plot. That's exactly what a scatter plot is for a correlation. A negative correlation is one where the number or the sign in front of the number is a negative. A positive correlation is where the sign in front of the number is positive. And a negative correlation occurs when one variable increases and the other variable decreases. Finally, you can have a situation where there's no correlation. What that means is your correlation coefficient is 0, and there doesn't seem to be a relationship at all between the two variables you are examining a relationship for. These graphs are from your textbook. They represent kind of correlations that the author of your textbook did. He assessed the relationship between the student's first test score and the final exam score, and he found a positive correlation. So what that means is if a student scored high on their first test score, it's also likely that they would score high on their final exam. He noted a negative correlation between the number of absences and the final exam score. The more absent a student was, the lower their exam score, right? Hopefully you can see kind of a downward trajectory here and an upward trajectory here. There's no relationship between the last 3 digits of the student's social security number and their final exam score. So you would end up with a correlation coefficient of 0 for this last scatter plot here. One thing to keep in mind when we're doing correlations and exploring the relationship between two variables is something called illusory correlations. Illusory correlations are correlations that look like they exist, but they really don't. So it's a correlation that doesn't exist, but for some reason we think it does because we're human beings and we are kind of biased to believe things that may not actually be true, right? We are more likely to have superstitions and believe in myths. And so illusory correlations kind of feed into that desire to believe things that are not real. So for example, there is no relationship between the full moon and abnormal behavior. If you've heard that there is, chances are it's an illusory correlation. Similarly, if you've heard that sugar tends to make people more hyperactive, this is also an illusory correlation, and they actually did a study to demonstrate that sugar does not trigger hyperactivity in children. They administered a placebo pill, which is not really a sugar pill, but it's a pill that contains no active ingredient. They administered it to all kids and asked their parents to evaluate hyperactivity in those kids. Half the parents were told that their kids received sugar, while the other parents were told that they did not receive sugar. Unfortunately, the parents who thought their kids received sugar claimed that their kids were more hyperactive. And so again, there was no difference in the kind of pill the kids got, but we tend to look for evidence for things to support our thinking and beliefs, even if it's not real. And so this represents an illusory correlation. The other element to keep in mind, and this is a big problem with correlations and the media, is that people tend to draw causal relationships between variables that are being correlated. A correlation simply tells you that there's a relationship between two variables. It does not tell you how or why they are related. You would actually have to conduct an experiment to determine how or why they are related. For example, I'm sure you've heard that diet contributes to heart disease. Unfortunately, these are all correlational studies. Changes in diet don't necessarily cause heart disease. There seems to be a relationship between diet and heart disease, but many people make causative conclusion or causal statements about the diet and heart disease. Perhaps the people that are more prone to heart disease end up eating more poorly, or vice versa. People who are less prone to heart disease may eat more healthy. And so when we have correlations, we cannot draw causative conclusions. Here's another example. You may have heard that people who are depressed also have impaired sleep. It may have been stated that people who are depressed or who have depression may sleep worse, or vice versa. It could be that impaired sleep may cause a depressed mood, but you could also have something called a third variable that influences both variables being correlated. Perhaps family conflicts cause both the depressed mood and impaired sleep. And that's why it's really important to not draw causative conclusions from correlations, because we really don't know how or why variables are related. And so when you hear about research that was conducted as a correlation and people are making causative statements about the relationship, a red flag should go off in your mind, because they're drawing the types of conclusions you cannot with a correlation. Experiments, so even though I call everything experiments, the only thing that you can call an experiment is a study that has a manipulation by an experimenter and another that is measured, right? So that's really a true experiment. When we manipulate, that means we change it in some way before we administer it to some participants and not others. That manipulated variable is called an independent variable. What we're measuring is called the dependent variable. So for example, if we're studying whether sleep deprivation negatively affects cognitive performance, in this particular example, sleep deprivation is being manipulated, so it's the independent variable, and we are measuring cognitive performance, so that's the dependent variable. We could imagine this study has people sleeping for 8 hours, 4 hours, or being completely sleep deprived, and all of them getting some sort of cognitive performance test. And so we are manipulating sleep deprivation by deciding how much sleep different subjects get. So this represents a true experiment. These experiments often also contain two groups or conditions. In fact, you can have more than two groups or conditions, but the idea is that we have a control condition, at least one, where the participant does not get the manipulated variable. Oftentimes, there may be more than one experimental variable, as I described for the sleep deprivation. In this example, the control condition would be getting 8 hours of sleep, and then the two groups of 4 hours or 0 sleep would represent the experimental conditions. You can, unlike correlations, draw causative conclusions from the results of experiments, but you can't draw causative conclusions from correlations. So if you're dealing with an experiment where an investigator or experimenter manipulated a variable and measured another, then you are likely to be dealing with an experiment, and the person can make causative statements about the results from that particular study. So this chart is from your textbook, and it represents kind of a summary of what I've just covered. observational studies and experiments and what makes them kind of what they are. We went in further detail about these types of ways to study human beings. And here is your summary of the entire lecture, not just the types of research designs. And then finally, here are your exit ticket questions. And that's all I got for you.